So, here is something worth sitting with for a quiet moment. Right now, wherever you happen to be, a clock may be showing a particular hour and minute. That number is a human invention. The moment itself is not. The earth is genuinely turning beneath you. The stars are moving through the dark. Your body is breathing, warming the air around it, and carrying out thousands of small processes without asking you to supervise any of them. Those things are real, but the decision to divide a day into hours, an hour into minutes, and a minute into seconds is something people had to imagine, build, argue over, and slowly standardize across thousands of years. The history of timekeeping is therefore not only the history of clocks, it is the history of how human beings learned to coordinate their lives with the sky, with one another, and eventually with the behavior of atoms. It begins with shadows and seasons. It passes through temples, monasteries, workshops, ships, laboratories, satellites, and equations. And along the way, the question changes. At first, people asked how to measure time. Much later, they began asking what time actually is. There is no need to hurry through that story. We can begin where everyone begins, by looking up. Long before anyone built a calendar, people noticed the great repeating rhythms of the world. The sun rose and set. The moon grew bright, thinned to a crescent, disappeared and returned. Warm seasons gave way to cold ones. Rivers rose. Animals migrated. Plants flowered and died back. These cycles were not abstract scientific ideas. They were woven into survival. They told people when to travel, when to plant, when to harvest, and when to prepare for winter. The most obvious cycle was the day, marked by the turning of the earth beneath the sun. The moon offered a longer rhythm, close to 29 and a half days from one full moon to the next. The seasons offered the year, but almost immediately, anyone trying to turn these rhythms into a calendar met a stubborn problem. They do not fit neatly inside one another. 12 lunar months are shorter than a solar year by roughly 11 days. A year is not an exact number of days. Nature provides cycles, but it does not arrange them into clean columns of arithmetic. So the earliest calendars were acts of negotiation. People inserted extra days, added occasional months, watched the sky, and corrected their systems when the seasons began to drift away from the names written on the calendar. The ancient Egyptians had an especially urgent reason to care. Their civilization depended on the Nile, whose annual floods spread dark, fertile silt across land that would otherwise have been desert. Knowing when the flood was approaching was not merely useful. It shaped the entire agricultural year. Egyptian observers noticed that shortly before the flood season, a brilliant star appeared low in the dawn sky after being hidden for many weeks. That star was Sirius, the brightest star visible at night. Its first appearance before sunrise, known as its heliacal rising, became a powerful seasonal marker. The sky was giving advance notice that the river would soon rise. The Egyptian civil calendar contained 365 days, 12 months of 30 days, followed by 5 additional festival days. It was simple, elegant, and extraordinarily useful. But the true solar year is slightly longer than 365 days. The difference is only about a quarter of a day. Yet small errors have patience. After 4 years, the calendar was about 1 day out of step with the seasons. After 40 years, about 10 days. Over centuries, the named months wandered through the entire solar year. The Egyptians knew that this was happening. They could watch the calendar drift away from the rising of Sirius and eventually return to alignment after roughly 1,460 years. In what later became known as the Sothic cycle, there is something quietly beautiful in that idea. A civilization living inside a calendar that slowly moved through the seasons, knowing that it would one day return to its starting place, though no living person would ever witness the complete journey. Far to the east in Mesopotamia, another ancient tradition left an even more direct mark on the clock beside you. The Babylonians used a number system based on 60. We call it sexagesimal. 60 is an unusually cooperative number. It can be divided cleanly into halves, thirds, quarters, fifths, sixths, tenths, and twelfths. That made it practical for astronomy, geometry, trade, and the subdivision of cycles. The Babylonian habit of thinking in 60s survived long after Babylon itself. It passed into Greek astronomy and through later mathematical traditions. It is the reason a circle has 360 degrees, an hour has 60 minutes, and a minute has 60 seconds. A choice made by scribes pressing symbols into clay tablets thousands of years ago is still present on digital displays, railway timetables, and the screen of a phone. For much of early history, astronomy and timekeeping were the same activity. The sky was the clock. Babylonian astronomers recorded eclipses, the paths of planets, and the positions of stars with remarkable patience. From generations of observations, they learned to recognize patterns and make predictions. Their models were not modern physics, but they allowed celestial events to be anticipated with impressive accuracy. Closer to the ground, the simplest timekeeper was a shadow. Place an upright object in sunlight, and its shadow changes direction and length as the sun moves across the sky. Obelisks and simple gnomons could divide the day into recognizable portions. Yet a sundial reveals something that modern clocks tend to hide. The hours of the ancient world were often not equal. In many societies, daylight was divided into 12 hours and darkness into another 12. Because summer days are longer than winter days, a daylight hour expanded in summer and contracted in winter. The third hour after sunrise did not correspond to one fixed modern time throughout the year. Time stretched with the season. To us, an hour that changes length may sound inconvenient. But if most work began with daylight and ended near sunset, it was perfectly sensible. The purpose of an hour was not to preserve an abstract quantity with mathematical purity. It was to organize the lived day. Sundials had an obvious weakness. They did not work indoors, at night, or beneath heavy clouds. Water clocks offered another solution. A vessel could be allowed to empty through a small opening, or water could drip steadily into a receiving container. Marks on the side showed how much time had passed. The Greeks called such a device a clepsydra, a name that can be translated as a water thief. The apparent simplicity concealed an engineering problem. Water flows faster from a full vessel because greater pressure pushes it through the opening, then slows as the level falls. Egyptian builders partly compensated by making some containers wider at the top and narrower below. As the rate changed, the shape helped the level descend more evenly. Without formal fluid dynamics, they discovered a practical correction. Through observation and repeated adjustment, water clocks regulated speeches in Athenian courts, marked military watches at night, and measured intervals when the sky was hidden. They were affected by temperature, impurities, and wear. But time could now be measured by a controlled process rather than only by a heavenly body. Around the 3rd century before the Common Era, Ctesibius of Alexandria developed a far more elaborate water clock. A regulated supply maintained a nearly constant flow. Water accumulating in a vessel lifted a float connected to a pointer, and the pointer moved across a dial. In some descriptions, the dial itself slowly adjusted through the year to account for the unequal seasonal hours. It was not merely a container with marks. It was a machine that converted flowing water into a changing display, an ancient analog computer devoted to time. Still, the old clocks were approximate. Water changed its behavior with temperature. Sundials vanished with the sun. Candle clocks burned unevenly. For ordinary life, this was usually enough. A person did not need to know that it was precisely 8 minutes past the hour. Dawn, midday, evening, and the sequence of familiar tasks provided all the resolution most people required. The next great demand for more reliable time did not first come from modern science or international commerce. It came from religion. In medieval Christian monasteries, the day and night were organized around regular periods of prayer. The rule of Saint Benedict prescribed a sequence of canonical hours, including prayers deep in the night and at dawn. Missing the proper time mattered. Yet, winter nights were long, skies were often hidden by cloud, and the monk assigned to keep watch could not always rely on stars, marked candles, or his own wakefulness. The earliest mechanical clocks grew from this need. They were not elegant household objects, and many did not have faces or hands. Their purpose was to release a mechanism and ring a bell. The word clock itself is connected to medieval words for bell. A clock was, before it was a display, a machine that caused a sound at the appointed moment. The central challenge was to control falling energy. Imagine a heavy weight hanging from a rope wound around a drum. Gravity pulls the weight downward, turning the drum in a train of gears. Left alone, the weight would simply fall and the gears would spin too quickly. A clock needed a way to let the mechanism move in tiny regular steps. That task belonged to the escapement. In the early verge and foliate mechanism, a toothed wheel was alternately stopped and released by small pallets attached to a rocking shaft. Each movement allowed the wheel to advance by one tooth. The suspended weight supplied the energy, while the escapement divided its fall into a repeated rhythm. Tick, then tock, then tick again. The foliate, a horizontal bar with adjustable weights, swung from side to side. It was not an especially stable oscillator. Friction, changing force, temperature, and wear could alter its rhythm. Early mechanical clocks might drift by 15 minutes or more in a day. By modern standards, that is enormous. By medieval standards, a machine that worked through darkness, rain, and winter was astonishing. Once installed in towers, these clocks changed more than the measurement of hours. A bell audible across a town created shared public time. Markets could open on a signal. Meetings could be arranged for a recognized hour. Gates could close according to schedule. Work could begin and end with a bell rather than with a private judgment about the position of the sun. This new social time also became a source of power. In textile towns, disputes arose over who controlled the work bell, because extending the measured day could mean extracting more labor. A machine developed to organize prayer became a tool for organizing commerce. The clock did not simply describe the rhythm of society. It helped impose one. The better heartbeat was discovered according to a famous story by a young student watching a lamp sway in a cathedral. Around the early 1580s, Galileo Galilei was studying in Pisa. During a service, he noticed a hanging lamp moving back and forth. The wide swings seemed to take almost the same amount of time as the smaller swings that followed. With no precise watch available, Galileo compared the motion to the beat of his own pulse. A pendulum has a natural rhythm. Its period depends mainly on its length and on gravity. A longer pendulum swings more slowly. A shorter one swings more quickly. For modest angles, changes in the width of the swing have surprisingly little effect on the timing. This near regularity is called isochronism. Galileo explored the idea and later imagined using a pendulum to regulate a clock. Near the end of his life, blind and living under house arrest, he described a design to his son, Vincenzo, but the device was never successfully completed. The first practical pendulum clock was built by another great 17th century scientist, Christian Huygens. Huygens understood that the pendulum could become the authority inside the clock. The falling weight would still provide energy, and an escapement would still count the motion. But the gears would now be forced to follow the pendulum's naturally determined pace. In 1657, a clock built to Huygens's design by Salomon Coster achieved an accuracy of roughly 15 seconds per day. That was an enormous improvement. The older tower clocks could lose or gain many minutes. The new pendulum clock reduced the daily error by about a factor of 60. Suddenly, astronomers could time celestial events more carefully. Experiments could be measured in seconds rather than vague portions of an hour. Precision began to enter ordinary mechanical timekeeping. Further improvements followed. The anchor escapement interacted more gently with the pendulum and allowed it to swing through a narrow arc, where its timing was more consistent. Long pendulums, including the familiar 1-second pendulum of a tall case clock, brought daily errors down to only a few seconds in the best instruments. But the pendulum had one severe limitation. It needed a stable floor and a reliable downward direction. On a ship rolling through the Atlantic, the deck tilted, rose, and fell beneath it. The very motion of the vessel interfered with the motion meant to measure time. A beautiful solution on land became nearly useless at sea. And by the 17th century, the sea had created one of the most urgent scientific problems in the world: longitude. A sailor could estimate latitude, the north-south position, by measuring the height of the sun at noon or the altitude of familiar stars. Longitude, the east-west position, was much harder. There is no equivalent fixed marker in the sky that directly reveals how far east or west a ship has traveled. The solution, in principle, was time. The Earth turns through 360 degrees in 24 hours, or 15 degrees in 1 hour. If a navigator knows local time from the sun and also knows the exact time at a reference port, the difference between those two times reveals the longitude. If local noon occurs when a clock set to the home port reads 2 in the afternoon, the ship is 30 degrees west of that port. The idea was simple. The required clock was not. It would have to preserve the time of the home port through weeks of rolling seas, changing temperature, damp air, salt, vibration, and the slow changes in a wound spring. A daily error of only 1 minute could place a ship tens of nautical miles away from its calculated position after a long voyage. In fog or darkness, that error could be fatal. In October 1707, A British fleet under Admiral Sir Cloudesley Shovel was returning from the Mediterranean. Navigators believed the ships were safely west of the Scilly Isles, a chain of dangerous rocks near the southwestern edge of England. They were mistaken. 4 ships struck the islands, and perhaps 1,500 to 2,000 men died. The disaster was not caused by a single missing clock, but it became a powerful symbol of the deadly uncertainty of ocean navigation. In 1714, the British Parliament passed the Longitude Act. It established a board of longitude and offered rewards for a practical method of determining longitude at sea. The largest prize, £20,000, was an extraordinary fortune. To earn it, a method had to determine longitude within half a degree after a voyage to the West Indies. Many leading astronomers expected the answer to come from the heavens. The lunar distance method used the changing position of the moon relative to stars as a kind of celestial clock. With accurate observations, detailed tables, and difficult calculations, it could reveal the time at a reference meridian. The idea was scientifically respectable. The alternative, a mechanical timekeeper that remained accurate on a ship, seemed to many experts almost impossible. Then John Harrison arrived. Harrison was born in 1693 and grew up in northern England, the son of a carpenter. He had no university education and no place among London's scientific elite. He learned by reading, observing, and building. His early wooden clocks were so carefully made that some ran with remarkable accuracy and needed little lubrication. He approached timekeeping not as a theorist seeking elegance on paper, but as a craftsman who expected every material to reveal its weaknesses under use. He understood that a sea clock had to survive several enemies at once. The motion of a ship disturbed oscillators. Heat expanded metal, cold contracted it, and those tiny changes altered the rate of a clock. Lubricating oil thickened, thinned, collected dust, and decayed. Springs delivered more force when fully wound than when nearly exhausted. Every imperfection that seemed trivial for a household clock could accumulate into a disastrous navigational error. Harrison's first marine timekeeper, now called H1, took about 5 years to build. It was a large brass machine with 2 linked balances moving in opposition. A disturbance pushing one could be countered by the other. Rather than requiring the ship to remain still, Harrison tried to cancel its motion within the mechanism. He also reduced friction and temperature error. Bearings made from naturally oily lignum vitae needed little added lubricant. In his land clocks, alternating metals expanded against one another in a gridiron pendulum, helping its effective length remain nearly constant as temperature changed. In 1736, H1 traveled to Lisbon. On the return voyage, it performed well enough that Harrison was able to disagree with the ship's navigator about the approaching landfall. The clock's prediction proved better. It was a dramatic demonstration, but Harrison did not claim the full prize. He believed the machine could be improved. H2 was more refined, yet Harrison found a weakness in its balanced design and abandoned the approach. H3 then occupied him for nearly 2 decades. During that effort, he developed further temperature compensation, including the bimetallic strip, in which 2 joined metals bend predictably as temperature changes. H3 was a remarkable machine, but it never fully satisfied him. Then Harrison's thinking changed direction. Perhaps the answer did not have to be a massive mechanism protected from every motion. Perhaps it could be a very accurate watch. Portable watches of the time were not generally precise enough for navigation, but Harrison had seen evidence that a smaller, faster balance could be less vulnerable to the slow motion of a ship. He began concentrating decades of experience into a device only about 5 inches across. The result was H4. From the outside, H4 looked like an unusually large and beautifully finished pocket watch. Inside, it was an accumulation of solutions: a rapidly oscillating balance, carefully controlled force, temperature compensation, refined bearings, and components made to a degree of precision that pushed 18th century craftsmanship to its limits. In 1761, H4 was carried to Jamaica aboard HMS Deptford. Harrison, then in his late 60s, did not make the voyage. His son William accompanied the watch and was responsible for its care. The crossing lasted 81 days. At the end of the voyage, the accumulated error of H4 was only about 5 seconds. The standard for the Great Prize allowed roughly 2 minutes. Harrison's watch had exceeded the requirement by an extraordinary margin. It should have been the clean ending to a long story. The clock worked, the longitude could be found, and the inventor received his reward. Instead, the struggle continued. The Board of Longitude demanded further trials. It required Harrison to reveal the details of the mechanism so that others could reproduce it. Partial payments were made, but the full reward was withheld. Some caution was understandable. A national navigation system could not depend on a single irreplaceable object, but the process was also shaped by rivalry, institutional pride, and a deep preference among influential astronomers for the lunar distance method. Neville Maskelyne, the astronomer royal and a leading supporter of lunar distances, also influenced the evaluation of Harrison's work. H4 performed less well in tests at the Royal Observatory than it had at sea. Harrison believed it was being handled unfairly. Whatever the full truth, the institution judging the mechanical solution was closely tied to supporters of its main competitor. Harrison eventually appealed directly to King George III. The king took an interest in the case and supported an independent test of another Harrison watch. According to the results, it kept time to within roughly a third of a second per day. The king reportedly declared that Harrison had been treated unjustly and should finally receive satisfaction. In 1773, Parliament awarded Harrison £8,750, bringing his total payments close to the value of the original prize. The Board of Longitude never formally declared him the winner. Recognition came indirectly, late and only after decades of resistance. Harrison was about 80 years old. He died 3 years later. His achievement reached far beyond one award. He proved that a mechanical clock could remain accurate through an ocean voyage. Marine chronometers, based on the principles he helped establish, gradually became essential instruments. Navigators could carry the time of a reference meridian across the sea, compare it with local noon, and locate themselves east or west with a reliability earlier sailors could hardly imagine. A clock had become a map, yet even the finest chronometer remained mechanical. Springs flexed, surfaces wore. Temperature compensation could reduce change but never erase the physical complexity of a machine. As science moved into the 19th and 20th centuries, researchers began searching for a rhythm more fundamental than a swinging pendulum or a balance wheel. Every clock, after all, counts repetition. The earth turns, a pendulum swings, a balance rocks. A quartz crystal vibrates when electricity is applied. The natural question was simple: what in the universe repeats most reliably? By the early 20th century, physicists had discovered that atoms interact with electromagnetic radiation at sharply defined frequencies. These frequencies are not chosen by a clockmaker and do not depend on the shape of a handmade spring. They arise from the structure of the atom and the constants of nature. Atoms of the same kind provide the same transition wherever they are prepared correctly. In the 1930s and 40s, Isidore Isaac Rabi developed molecular beam magnetic resonance, a method for measuring atomic transitions with great precision. A beam of atoms passed through magnetic fields and was exposed to radiation. When the applied frequency matched the natural resonance of the atoms, their quantum state changed in a detectable way. And the principle was rather like tuning a radio, until a faint signal suddenly became clear. Rabi recognized that an atomic resonance could serve as the regulator of a clock. Instead of asking a pendulum or spring to preserve its rhythm, a feedback system could continually adjust an electronic oscillator until it matched the atom. In 1955, Louis Essen and Jack Perry built the first operational cesium atomic clock at the National Physical Laboratory in England. Their instrument used cesium-133. Microwaves were directed at cesium atoms, and the apparatus searched for the frequency that caused the strongest transition between two closely spaced energy states. If the frequency drifted, the response of the atoms revealed the error and allowed the oscillator to be corrected. That resonant frequency is 9,192,631,770 cycles per second. Essen's first clock was accurate to roughly 1 second in 300 years. Harrison had reduced a long sea voyage to a few seconds of error. The cesium clock reduced centuries to about the same scale. The leap was not achieved by perfecting mechanical craftsmanship. It came from replacing the crafted oscillator with a feature of nature. Every suitable cesium atom offered the same reference. A laboratory in one country could reproduce the standard used by a laboratory somewhere else. In 1967, the international definition of the second was changed. Instead of being derived from the rotation of the Earth or a fraction of the year, 1 second became the duration of exactly 9,192,631,770 periods associated with the chosen transition in cesium-133. The number was selected so that the atomic second continued the older astronomical second as closely as possible. But the philosophical shift was enormous. For most of history, humanity had defined time by looking outward at the sky. Now the basic unit of time was defined by looking inward, into matter. Atomic clocks soon became precise enough to reveal something that earlier clocks could barely approach. Time itself does not pass at one universal rate. Albert Einstein's special theory of relativity says that a moving clock accumulates less time than a clock at rest relative to an observer. His general theory of relativity says that gravity also changes the rate of time. A clock deeper in a gravitational field runs more slowly than one higher up, where gravity is slightly weaker. These are not errors caused by poor instruments. Any clock would show the effect: mechanical, atomic, chemical, or biological. Different paths through space-time can contain different amounts of elapsed time. In 1971, Joseph Hafele and Richard Keating carried cesium clocks around the world on commercial aircraft, once eastward and once westward, then compared them with clocks that had remained at the United States Naval Observatory. The differences were measured in nanoseconds, but they followed the combined predictions of motion and gravity. A philosophical claim about the nature of time had become something that could be checked with airline tickets and clocks placed on passenger seats. The most familiar practical demonstrations is the Global Positioning System. Satellites orbiting more than 20,000 kilometers above Earth carry atomic clocks and broadcast carefully timed signals. A receiver compares the arrival times from several satellites. Because radio waves travel at the speed of light, a difference of only a few billionths of a second corresponds to a measurable difference in distance. From those differences, the receiver calculates its position, but the clocks in orbit do not naturally remain synchronized with clocks on the ground. The satellites move quickly, so special relativity makes their clocks run about 7 microseconds per day slower. They are also high above Earth, where gravity is weaker, so general relativity makes them run about 45 microseconds per day faster. The gravitational effect is larger. The net result is about 38 microseconds of extra time per day for the satellite clocks. 38 microseconds is far too small to notice in ordinary life. Yet light travels more than 11 kilometers in that interval. Without relativistic correction, GPS positions would drift by roughly 10 kilometers each day. Maps on phones, aircraft navigation, surveying, emergency dispatch, and precision agriculture all depend on accounting for the fact that time passes differently in orbit than it does on the ground. Cesium clocks continued to improve, especially with the development of atomic fountains that gave atoms more time to interact with microwave radiation. But researchers eventually turned toward optical transitions. Visible and near-visible light oscillate tens of thousands of times faster than the microwaves used in cesium clocks. A faster oscillation offers a finer set of marks with which to divide a second. Optical frequencies were long too rapid to count directly. The bridge was the optical frequency comb, associated especially with Theodor Hensch and John Hall. An ultra-fast laser produces many evenly spaced frequencies, like the teeth of a comb. Their spacing can be measured electronically, turning the comb into a ruler that connects ordinary counters to light oscillating hundreds of trillions of times per second. That tool enabled clocks based on optical transitions in strontium, ytterbium, aluminum ions, and other atoms. Some trap thousands of neutral atoms in a lattice of laser light. Others isolate a single ion and monitor it with extraordinary care. Their designs differ, but the purpose is the same: to lock a laser to a transition that is narrower and faster than the microwave transition of cesium. The finest optical clocks reach uncertainties corresponding to about 1 second over tens of billions of years. Their precision is so great that raising one clock by about a centimeter can produce a detectable difference in its rate. The higher clock sits in slightly weaker gravity and therefore ticks slightly faster. Because optical clocks have surpassed the cesium standard, metrologists have been preparing for a future redefinition of the second based on an optical transition. Such a change requires careful international comparisons. A unit used by science, navigation, communication, and industry must be reproducible across laboratories, not merely demonstrated by one exceptional machine. Meanwhile, The official time used by society has faced an awkward problem. Atomic time advances uniformly, but Earth's rotation does not. Tides slowly alter the length of the day. Winds, currents, earthquakes, and movements within the planet add smaller, irregular changes. Civil time is expected to remain close to the sun, yet its atomic foundation is steadier than the turning Earth. Since 1972, leap seconds have occasionally been added to coordinated universal time. At the chosen moment, a clock can pass from 23:59 to 23:59:60 before reaching midnight. The extra second keeps civil time close to the astronomical day. This correction is troublesome for software because many systems assume every minute has exactly 60 seconds and timestamps always increase simply. An extra second can confuse databases, networks, and financial systems. In November 2022, the General Conference on Weights and Measures agreed that the present rule should change. It asked international timekeeping bodies to prepare a plan for increasing the permitted difference between Earth rotation time, known as UT1, and Coordinated Universal Time in or before 2035. That year is an implementation deadline, not a promise that the final leap second will occur exactly in 2035. The new tolerance and the method for handling the accumulated difference still require further international agreement. There is a quiet symbolism in that decision. The sun was humanity's first clock. Now our shared time is increasingly allowed to follow atoms instead. Yet every instrument in this story, from a sundial to an optical lattice clock, measures time without explaining what time is. A thermometer can measure temperature without telling us why temperature emerges from moving particles. In the same way, a clock compares change with repeated change. The deeper question remains. Einstein approached the problem by asking what it means for distant events to happen at the same time. Imagine lightning striking both ends of a railway platform. An observer at the center receives both flashes together and calls the strikes simultaneous. An observer on a fast train moves toward one flash and away from the other, receiving the forward flash first. It is tempting to say, the train observer simply saw the events incorrectly. But neither observer has a privileged state of rest, and the laws of physics work consistently for both. With light traveling at a finite speed, simultaneity at separated locations depends on motion. There is no universal clock assigning one unquestioned present to the whole cosmos. This relativity of simultaneity leads naturally to time dilation. Two people who separate move differently, and reunite may have experienced different amounts of time. In the famous twin example, one twin travels at a speed close to that of light and returns younger than the twin who stayed behind. The traveling twin's heart, cells, and clocks have all accumulated less time along that path. General relativity goes further. Space and time form a connected geometry called spacetime. Matter and energy curve that geometry, and free objects follow its curves. Gravity is therefore not simply an invisible force acting across an empty stage. It is connected to the shape of the stage itself. Differences in clock rate are part of that geometry. Near a black hole, the contrast becomes extreme. A distant observer sees signals from a falling object slow, dim, and redden near the event horizon. For the falling observer, local time continues normally, and the horizon may be crossed without a special instant being felt. Different paths through spacetime support different descriptions of elapsed time. General relativity is extraordinarily successful, but it does not fit comfortably with the other great framework of modern physics, quantum mechanics. In general relativity, time is dynamical. It bends with space-time and depends on matter. In ordinary quantum mechanics, time usually appears as an external parameter, a background variable telling the quantum state when to change. Position and momentum are quantum observables. Time is treated differently. This mismatch lies near the heart of the search for quantum gravity. Approaches such as string theory, loop quantum gravity, and causal set theory attempt to describe situations where both gravity and quantum affects matter. None has yet provided a universally accepted final account of time. Some proposals suggest that time may not be fundamental. It may emerge from relationships among parts of the universe, much as temperature emerges from the collective behavior of many molecules. At the level of one molecule, temperature is not an independent substance. It becomes meaningful when many microscopic motions are described together. Perhaps time has a similar status. The Wheeler-DeWitt equation, developed in early work on quantum gravity, makes the puzzle especially vivid. In a simplified description, it attempts to represent the quantum state of the entire universe. Yet the usual time variable does not appear. The universe seems mathematically timeless, even though change fills our experience. One proposal associated with Don Page and William Wooders suggests that time can emerge through quantum correlations. One part of a system can function as a clock relative to another. To an observer inside the system, events unfold in sequence. From an imagined view of the entire isolated state, the description may remain static. This is an intriguing framework, not a settled answer. There is another mystery that is even closer to everyday life. Whatever time is, it seems to have a direction. We remember yesterday and not tomorrow. A cup falls and breaks, but scattered pieces do not leap together. Warm coffee cools in a room, but room temperature coffee does not spontaneously gather heat and begin to steam. This direction is called the arrow of time. It is puzzling because many fundamental equations work almost equally well forward and backward. A recording of two ideal billiard balls colliding could be reversed and still obey Newton's laws. The basic dynamics often do not contain an obvious command saying that the future must point one way. Thermodynamics supplies the strongest explanation. The second law says that the entropy of a closed system tends to increase. Entropy is sometimes described as disorder, but more precisely, it reflects how many microscopic arrangements correspond to the same large-scale appearance. A deck sorted perfectly by suit and number has very few arrangements that look exactly that organized. A shuffled deck can take an enormous number of arrangements that all look random. When the deck is mixed, it almost certainly moves from the unusual ordered state into one of the countless disordered states. It is not that nature has a preference for mess. There are simply overwhelmingly more ways to be mixed than sorted. The same statistical imbalance appears when perfume spreads through a room, when ice melts, and when coffee cools. The microscopic laws could permit fantastically unlikely reversals, but the number of arrangements corresponding to equilibrium is so immense that the reverse is effectively never seen. Entropy, therefore, gives everyday time its direction. Records, memories, aging, cooling, and irreversible processes are all connected to the fact that the universe is moving from lower entropy conditions toward higher entropy ones. But this answer opens another question. If entropy tends to increase, why was it low enough to increase in the first place? Observations suggest that the early universe was extraordinarily smooth. The cosmic microwave background, the faint afterglow of the early cosmos, is almost uniform, with tiny variations that later grew into galaxies and clusters. Although the early universe was hot, its smooth gravitational arrangement represented a very special low-entropy state. The idea that the universe began in such a condition is often called the past hypothesis. Combined with statistical mechanics, it explains why entropy is lower toward what we call the past and higher toward what we call the future. But it does not explain why the initial condition was special. That question remains open. Roger Penrose and others have proposed ideas about the restricted gravitational structure of the early universe. Other cosmological models seek an explanation in inflation, quantum creation, or broader cycles. These possibilities are speculative. They remind us that even after learning to measure time to fractions beyond ordinary imagination, physics has not fully explained why time has the character we experience. And perhaps that is an appropriate place to begin returning from the edge of the unknown. Human beings first followed the sun, the moon, the river, and the seasons. Egyptians watched Sirius rise before dawn. Babylonians divided cycles with the number 60. Water dripped through carefully shaped vessels. Monks listened for bells in dark stone monasteries. Pendulums swung beneath clock cases, and Harrison's watch carried the time of home across an ocean. Then the rhythm moved inside the atom. Cesium defined the second. Optical clocks counted light with such precision that the height of a table mattered. Satellites corrected their time for speed and gravity, so that a small receiver on Earth could discover where it was. Through all of that, clocks became better and better at comparing one change with another. Yet the oldest experience remained unchanged. One breath follows another. The room slowly cools. The night deepens. Somewhere, tower clocks still move gears and ring bells. Quartz crystals vibrate inside ordinary watches. Standards laboratories compare atomic clocks to maintain the time used by communication networks and navigation systems. In quiet experimental rooms, lasers probe atoms hundreds of trillions of times per second, searching for ever smaller differences. Beyond those laboratories, Earth continues its slightly irregular rotation. The moon raises tides and slowly alters the length of the day. The solar system moves through the galaxy. The universe expands, cools, and develops along the arrow established by its distant beginning. None of this requires you to count the seconds tonight. The clocks can do that. They can divide the hour, preserve the time of distant places, correct for curved space-time, and maintain a shared rhythm across the world. You only need to notice the simpler rhythm that was here before every clock. A breath arriving, a breath leaving, the body settling more heavily into rest. Time has been a shadow, a stream of water, a falling weight, a swinging pendulum, a balance wheel, a microwave resonance, and a line of laser light. Or perhaps those have only been mirrors in which we watch change passing. Modern timekeeping also created a new kind of invisible dependence. Today, time is not only something shown on a clock, it is part of the hidden structure of civilization. Banks need precise timestamps. Power grids need synchronized signals. Stock markets, satellites, phone networks, emergency systems, computer servers, scientific instruments. and global navigation all depend on clocks agreeing closely enough that the modern world does not drift into confusion. This is why atomic time matters so much. The second is no longer defined by the swing of a pendulum or the rotation of Earth alone. It is defined by the behavior of atoms, because atoms offer a rhythm far more stable than anything mechanical. A clock based on atomic transitions can keep time with a precision that would have seemed almost supernatural to earlier generations. But there is a quiet irony here. The more precisely we measure time, the more clearly we see that nature does not provide one simple human clock. Earth's rotation is not perfectly uniform. The moon pulls on the oceans. The planet's interior shifts. Winds, ice, earthquakes, and long-term tidal effects all slightly affect the spin of the world. The day feels steady to us, but in the language of precision timekeeping, Earth is a beautiful but imperfect clock. So modern society lives between two kinds of time. There is atomic time, regular and extremely precise, and there is astronomical time, tied to the turning of Earth and the position of the sun in the sky. Keeping civil time connected to both has required adjustments, debates, and systems that most people never notice. Computers added another layer. A digital system does not experience time the way a human does. It counts. It stores timestamps. It compares sequences. It asks which event came first, whether a certificate has expired, whether a transaction is valid, whether a message arrived too late. In a networked world, time is not just philosophical. It is security, coordination, memory, and order. And inside each human body, there is still another clock. The circadian rhythm does not tick like a watch, but it shapes sleep, alertness, temperature, hormones, digestion, and mood. Light entering the eyes helps set this rhythm. Darkness tells the body another part of the story. When artificial light, screens, shift work, travel, stress, or irregular sleep disturb that rhythm, the body may still function, but it may feel less settled. So, the history of time is not only about measuring the universe. It is also about learning how deeply rhythm lives inside us. Either way, the moment continues without needing to be named. The earth turns. The stars move. Entropy rises quietly. And the long history of timekeeping carries on somewhere beyond the room, leaving you free to stop measuring for a while. So let the numbers on the clock take care of themselves. Let the next minute arrive without waiting for it. Let the pendulum slow in your imagination. The bell fade across the distance, and the moving shadow disappear into night. Time will continue doing what it has always done, and for now, it can carry you softly into sleep.